Hello, my name is Bjorn Kvale. I'm a product marketing engineer at Nordic Semiconductor, and I will be the host of this webinar. Together with me, I have Kate Stewart, Carlos Kufi, and Marty Bolivar. Kate Stewart is from the Linux Foundation, and Carlos and Marty both work at Nordic Semiconductor. Kate will start, and she'll talk a bit about sort of a higher level overview of Zephyr first, and then Carlos and Marty will take a deep dive. So they'll do a bit more technical depth, and then Marty will have a demo at the end. Feel free to post questions in the chat in the bottom right-hand corner. It will be roughly a 50-minute presentation and then a 10-minute Q&A. But we will try to we'll try to answer questions as the presentation is going. And also one last thing, the recordings and the presentation will be available after the webinar, and I'll post that in the chat too. So without further ado, let's start this Zephyr RTOS intro webinar. Thank you.
Good day. My name is Kate Stewart, and I'm with the Linux Foundation, and I'm here today to give you a bit of an overview about what's happening with Zephyr. And then my colleagues in the Zephyr project, Carlos Kufi and Marty Bolivar from Nordic, will be giving you a bit more details about the technology inside Zephyr. And so with that, I just want to give you a bit of a background for what we're doing. Zephyr was started about in early 2016. We launched publicly, but the code base work started in 2015. So we've been around for about 5 years now. And right from the start, we wanted it to be an open source project with neutral governance and permissibly licensed so that we can build a community. And 5 years later, we've got more of a community now. And we're sort of starting to execute and see some of the goals that we wanted to achieve at the start starting to happen, which is really exciting. And there'll be some more coming up next year too. But we started this project off with making sure we go after the safety certifications and security certifications, as well as other certifications for that matter. And we wanted to make sure that we had a broad base that multiple architectures could participate in. In some cases, we wanted to have a solution for where when Linux was just too big, we wanted to be able to have the same level of quality and the same rigor that we see in Linux in some of these disciplines, so that we have a good environment for developers to work in, as well as a sound basis for products to be coming up from. And we've been seeing the products emerging now. The last couple of years, we've seen more and more showing up. Given it's an embedded RTOS, we don't always know where it is. It's sometimes, a bit of a detective game and talking to people and to try to figure all these things out. But in the last 6 months, we've seen, 3 products we found out about, the distancer, the Centrios, and safety pods, all helping people with the whole COVID situation in terms of, tracking with Centrios, and then also the distancer to make sure you're within a certain period of time. And this comes in addition to some of the products that we've already seen coming in with Zephyr. Things like, I guess, the Adero is on here. It's a tracking device. And so you can have tags and taglets. Again, low powered constrained devices is where we want Zephyr, where Zephyr is targeted towards. But we also see cases where, we're going to have to care about battery life and things like that. And so this Gnar box is something I'm using since I'm a photographer when I'm not, working on tech, I'm working in photography. So I was sort of excited when that product came out. And then it had Zephyr, it was like, oh, bonus. So it's like, okay. So there's a lot of cool things that are emerging and Zephyr. And so it's an exciting time for the project. Zephyr is supported on multiple hardware architectures. And so this is something that was an initial goal, and I think we've done a pretty good job of achieving it. We initially were aiming it more like at the M cores. We've got also the R and A cores from ARM. We've got x86 and 32 and 64-bit. Same with 32 and 64-bit RISC-V, as well as ARC has good coverage with Zephyr, and they're a very active part of the community from Synopsys. And then there's a NIAS2 processor and the Tensilica as well. All those are in the code base today. And there's some pull requests open for bringing in the open power architecture to be running via FPGAs. Actually, it's kind of cool, as well as the Spark architecture. So we're seeing, and it's open for any architecture that you would like to add into Zephyr, just working with the community to get it upstream and making sure we have a maintainer for it. And if it works in those constraints, then I think it's likely to get in. One of the things that's really cool right now is we're finally starting to see development board shipping with Zephyr. The first one that was pretty visible was sort of the PhyTech real board, but in the last year, Nordic the E91 that just came out last year is now shipping with Zephyr by default. So products based on that are likely to have Zephyr in it as a starting point. And there's others that we're starting to emerge. So I'll be trying to update this slide soon. In fact, we've got over 200 boards now with Zephyr. And having all these boards available, gives developers a wealth of options to use as a starting point for creating products. When we started Zephyr off, though, that pace of change was sort of on the other side of the spectrum from what we needed for like safety certifications. And so we came up with this model of we do development in a very much an iterative upstream flow. And then every 2 years, we'd cut an LTS. And so the long-term support kernel or stable, as we call it, is what we recommend for people to use for making products. Bug fixes go into the upstream development and are backported into the stable releases. And then we're also looking at taking that stable now that came out last year and subsets of that, as well as what's happening upstream, are being used to sort of figure out what we're going to create for an auditable version next year. And so the auditable will be a subset of that LTS next year. But we're in the process of putting all these pieces together right now. So it's exciting days when you start to see what's happening in the community. The LTS, when we came out with it last year, was our LTS 1, and it's actually was the 1.14 release, but it's our LTS 1. And it is product focused, but it is kept current with the security updates. That's the key part. And it is compatible with new hardware. So if there's a new hardware that makes sense to add in, that discussion can be opened up with the community. And it is tested and has the same sort of testing and rigor that we want to have for Zephyr. It's important though, it's not a feature release. We're not going to put the latest shiny in there. We're going to keep it stable for people to build products off of. If you need a new feature and it's only up in the upstream, that's your best option. But if you have everything you need in the LTS, that's where we recommend. We've actually put out updates against the LTS. It has, we've had 2 releases up till now, and there's a 3rd getting queued up. And in these releases, we have things like our Bluetooth certifications that we've achieved as a project, as well as our vulnerability, so that issues that have been fixed that are listed by their CVE numbers. So, and a lot of other bug fixes that have been added, found and fixed. But Zephyr is, very much focused on the development is for the latest and greatest, and then stable is for something that we can use for products. Part of the challenge, obviously, when you're putting products out, though, is that bugs happen. Bugs happen in open source. The bugs happen in real source. Bugs happen in the commercial sources as well. And it's how we work with it and how we fix it. I think that we're starting to become one of the first-class citizens and try to use some best practices for this. One of the things we did is we got a really good boost on our processes when we revised them earlier this year to because we got a bulk vulnerability report from NCC Group, which we're very thankful for. And this helped us figure out how to tune our processes better. Up to that point, we've been seeing like maybe one vulnerability a quarter, or maybe 2 max. So it was a fairly low flow. And then all of a sudden we saw this good big bulk of them. And so we got to do some changing. One of the things we obviously did was update our documentation and make sure that everything was reflecting what we were doing as a project. And we have secure development, secure design, and security certifications in mind behind this. And it's an ongoing process. As we adjust and change, we'll try to reflect it into the documentation and keep everything up to date. One of the things we're pretty proud of is the fact that Zephyr is one of the few open source projects that is actually listed as a CVE numbering authority with MITRE. And we have a PCERT team, a project security incident response team that's looking at vulnerabilities coming in on an encrypted basis. And if you go to MITRE's site and you look at the CNAs, you will see Zephyr's project listed along with information about our vulnerability disclosure, as well as any advisories that are out there. Now, I was referring to earlier about this bulk report that made us basically, re-examine what we're doing and refresh it and sort of tune it up. There was 26 issues there, and most of these issues, ended up with one CVE or multiple. And everything is now public because our embargo window is passed. And so you can take a look at this online if you're interested in more details. Some of the results from the report were, we've pretty much fixed in fact, all the issues have been fixed in one way or the other, except for one that we recommend you disable. One of the things that came out of it, though, is we re-examined our embargo policy, and we decided it wasn't fair for product makers to only have 30 days to fix it. So we've extended it to be 90 days. And so we have 30 days for the team to work on it, and then another 60 days for notifying our product makers that have Zephyr in them, so they can decide if they need to remediate or not. And we'll be continuing to improve the process over the years to come. There's also, for product makers, a way that they can register for the vulnerabilities, and so that they can be notified within that embargo period I was talking about. So product makers who have a product that's visible in public want to register, all they need to do is click on the link and register, and then we will notify them as a project during the embargo window when there's new vulnerabilities so that they can remediate too. These sorts of practices, as well as the quality of the code, have pretty much got Zephyr to be #1 now in terms of the total commits that are there, and that's only possible because we've got over 700 contributors that we've seen working into the repo. So we're #1 as well in this RTOS landscape, which is kind of exciting. And if you look at the actual stats and traffics, you're going to see that in a 2-week period, there's been over 2,000 people uniquely cloning Zephyr and downloading that information, like downloading the repo. In fact, there was over 14,000 clones, but there was 2,000 unique cloners. So there's a lot of activity going on. People are downloading it, using it, and they're doing it for purposes. And the challenge, because it's embedded, is we can't quite, which products are they building? How are they doing it? These are the things that are making things interesting and challenging for us to figure out. But one of the things that's exciting is the fact that we have become very diverse in terms of the contributors that are upstreaming fixes and features and changes into the code repo. When we started, there was just a few, and now we have a significant number of companies that we can see contributing into the code repo, and various, well over 700 individual contributors have participated. That's when I checked the stats just yesterday. And we also have like over 44,000 commits right now. You can go see these stats on GitHub yourself. Everything is pretty open and pretty transparent that way. And there's now over 200 boards that you can use that have Zephyr on it. And those are in our repos as well. The community has been continuing to grow, and the bulk of the developers have, interact mostly on Slack. If you want to follow us on Twitter, there's the latest sort of release information and where people are going to be, meeting and talking about Zephyr. And as we learn about new products, we sort of make sure we let other people know about it there on Twitter, and as well as on LinkedIn. And there's also a WeChat group very active about letting people know about the changes in China too. And so with that, I'm going to turn it over to my colleague, Carl from Nordic, and he will basically go through more of the technologies in Zephyr and give you more of an overview of that. But I hope this was useful. Thank you.
Hi, my name is Carlos Cufi. I work for Nordic Semiconductor, and I'm here to give you a quick technology overview of Zephyr. Before we start with the actual technology, let's take a look at what the Zephyr ecosystem is. It's actually a bunch of different parts that together really make up what we call Zephyr today. So Starting actually from the bottom, we have the Zephyr OS. That's the real-time operating system that we know. We'll talk about it in detail in a few minutes. In the meantime, let's take a look at what we call the Zephyr project. So that would be actually everything around the operating system and the operating system itself, of course. But in fact, in the Zephyr project, we provide much more than just an RTOS. We actually build an SDK so that you have all the compilers you need to build for all the architecture supported by the RTOS. We provide tools like WEST, which will be talked about in depth later in this webinar. We also provide additional tools in a development environment. On top of that, there's also a bootloader, there's device management, and several other features that are part of what we call the Zephyr project. There's also the community. The community is actually very important to Zephyr. We have third-party modules and libraries. We have support for Zephyr in many projects now, Micro ROS, TensorFlow, MicroPython, JavaScript, and many more actually. So Zephyr is quickly becoming one of the platforms to port to when you have a project that can run on embedded systems. So with that said, let's talk a little bit about the Zephyr OS itself. So from a very top level sort of point of view, we can separate three different layers of it. There's the low level kernel and drivers, which essentially means the scheduler, the kernel synchronization objects and primitives, the kernel services, and all sorts of functionality that the actual kernel provides. There's also the low-level architecture and board support. They're actually different. The architecture code is the one that allows Zephyr to run in different ISAs or instruction sets. And then the boards, those are usually defined in terms of metadata and then some board-specific code. There's also power management hooks in the kernel and in the drivers, and of course, very low-level interfaces to hardware, sometimes direct, sometimes indirect through peripheral and hardware drivers. Then we come to the next layer, which can be described as the OS services and low-level APIs. So obviously you have platform-specific drivers. In some cases, those are not generic enough to warrant the addition of a generic API. So instead, we have a driver that's specific to a particular SoC or to a particular board. Then we have I/O APIs that come in many shapes and forms, file systems, of course, logging, debugging, IPC, which we'll talk about in more detail later, cryptography services, networking, and device management. And finally, the application services, which are very high-level APIs that allow the application to access standardized data, such as JSON and other formats that are common today. CBOR, for example, is being used more and more for embedded applications. And then we have high-level networking protocols such as HTTP and similar ones. So that describes a little bit the way the Zephyr sort of name is being used today in several contexts to describe the components that define the Zephyr RTOS and what it means. So let's now talk a little bit about how the actual code is organized. So I've tried to draw a small diagram here where you have the main repository and several ancillary or module repositories below. So the main repository is actually the one you can find in github.com Zephyr project RTOS Zephyr. This is what people traditionally call Zephyr. It contains all of the core Zephyr code, all of the code that has been written exclusively for Zephyr, that doesn't come from third parties, that actually was contributed with the idea of being part of Zephyr from the beginning, from its conception. Then all of it, or almost all of it, we still have some stragglers in there, but most of it is covered by an Apache V2 license. Then we have external repos, which we typically called modules. Those repositories contain several different things, but among them the vendor HALs. So that means, for example, in the case of ARM, the ARM architecture, the CMC HAL, the STM32 cube for STM-based microcontrollers, MCUX for NXP, NRFX for Nordic, and so on. We also have an external crypto implementations. We have Embed TLS, we have TinyCrypt and others. Then we have file systems that one can optionally bring in, actual file systems. We also have storage mechanisms that we'll describe later, but those live in the core repo. But when it comes to file systems, we have a choice of several. Among them, there's LittleFS and FatFS, both of them relatively popular in the embedded world. And then we have additional libraries, OpenAMP for asynchronous multiprocessing, asymmetric multiprocessing. We have LoRa for LoRa radios, LVGL for display, OpenThread, which enables the thread protocol over 15.4, CAN Open Node so that you can communicate via CAN, and several others. This distinction of having one core main repository named Zephyr, and then a bunch of other ones that are maintained externally. They're third-party projects, so they have their own life cycle, they have their own release schedule, they have their own way of building, their own CI. Everything is independent from Zephyr, and we import them but maintain our own copies of them inside the Zephyr project-RTOS GitHub organization. And we do that just so that we are sure that the contents of them cannot disappear, that revisions cannot suddenly vanish into thin air because someone has decided to force push, etc., etc. So then we have a meta tool that that has its own talk later in this webinar called West, that actually manages the repos and does much more. But you'll have to wait until that portion of the webinar comes. So let's talk a little bit about how Zephyr is organized in terms of the build and configuration systems. This might not seem like a big deal when dealing with RTOSes, or at least maybe it wasn't until now, but more and more developers are interested in knowing that the build and configuration system that they're going to use is actually not only powerful enough to configure and build an RTOS, but also that it can be reused for the application itself. Because the applications more and more are complex and require multiple configurations depending on the chip that they are on, depending on the target board and so on. So it's fundamental that one can reuse that, because one doesn't want to have multiple build and configuration systems, one for the RTOS and one for the application. So in Zephyr, we opted for standards or industry standard systems. One is CMake. You probably know that already. It's cross-platform. It's extensible. It's script-based. It's very powerful and used by many successful projects. So that's what gives us the ability to build, track dependencies, and so on. Then for configuring the project, we actually took kconfig, which is the Linux kernel's configuration system, and partially re-implemented it in Python. So we took an open source project that started doing that, and then the author actually started contributing to Zephyr, and we ended up with a almost fully featured in the end implementation of kconfig in Python, so it's cross-platform for Zephyr. And then finally, to describe the hardware, the choice we made is to use device tree, which is a standards-based hardware description language. So it has its own specification, and it's based on, or it has an open development model for that specification. But we use it a little bit differently than what is done, for example, in Linux. So all the references to the hardware are resolved at build time. There's no runtime detection of the hardware. Instead, everything is pre-processed and pre-programmed at build time. And then to access the device tree nodes and the properties, there is a macro-based API that you can use from your source code. So that gives you access to all of the instances of the different devices, buses, and so on. That's basically what we use in order to build and configure Zephyr. Next, let's talk a little bit about the architecture of Zephyr. So As you probably have guessed already, based on the previous slide, Zephyr is very configular and very modular. It has a lot of features, comparative and preemptive threading. It also relies on statically allocating the memory and resources. On most of the configurations we typically ship with, the memory, and the resources are predefined at build time. We don't use malloc or dynamic allocation of any kind. There's also memory protection, stack overflow protection, kernel and device driver permission tracking, thread isolation. There's support for Bluetooth Low Energy with both controller and host. There's open thread integration with support for 15.4 and also a native networking stack. So there's a lot of there to go through. Let's talk a little bit about the kernel and the drivers. So this is a very flexible and modern kernel. It supports both single core, symmetric multiprocessing, and asymmetric multiprocessing via an IPM driver, and also using OpenAMP. Again, an industry collaborative effort to provide libraries to enable asymmetric multiprocessing across devices. As mentioned, we have comparative and preemptible threads, a lot, and I really mean a lot. There's many synchronization and data passing primitives that you can choose from. Then there's user mode. That's what we were talking before when we talked about memory protection. It isolates user mode threads so that they cannot be harmful to other threads or to the kernel. And then all of the calls are validated through the system using the system call mechanism, just like with modern operating systems. There's also a very efficient device driver model, which means that we store everything that can be constant, that can be pre-calculated at build time, is stored in flash, so it doesn't need to be loaded into RAM. As you know, most MCUs have NOR flash that can be accessed directly without the need for preloading it into RAM. So we also have direct access to the device tree nodes, and then obviously common APIs for all hardware implementation. So if you want to write an application that uses SPI, you don't have to write it several times. You write it once and compile it for different platforms. We also have a native IP stack. It was actually originally developed based on the Contiki IP stack, but then that was scratched and a new one was built from scratch for Zephyr and using all of the Zephyr kernel primitives and written in a style that matches and the way the Zephyr kernel works. So it has a lot of features. I'm not sure if it's worthwhile going through them all, but essentially if you're looking for an IP stack feature, you probably will find it, and if you don't, then it's likely that someone is working on it or has plans to work on it, because the development of the networking stack is very active and there are a lot of contributors today working to make it better. Next, let's talk a little bit about the protocols that we support when using networking. So we have the usual suspects, CoAP and MQTT, HTTP, and LWM2M. Obviously also Thread, thanks to the very tight cooperation between the Thread project and Zephyr. We have a very good integration with it, as mentioned. And then when it comes to physical layers, we have Ethernet, then Ethernet over USB, which is supported natively on Linux and on Windows. Then Wi-Fi, but that's with IP offloading. We don't really have a Wi-Fi stack yet. We have 15.4 with 6LoWPAN, Bluetooth Low Energy with 6LoWPAN, so you can create a TCP/IP link over Bluetooth Low Energy. We also have CAN bus, with 6LoWPAN, PPP, so if you can want to create a point-to-point link, and the serial modem interface to interface with popular modems via AT commands and data streams. The Bluetooth host and mesh implementation in Zephyr has been in development almost since the beginning, and it's one of the most worked on and most active communities, sub-communities, I would say, in Zephyr. It is compliant with the Bluetooth 5.1 and 5.2 specification, actually. It mainly focuses on Bluetooth Low Energy. It supports multiple HCI transport, so you can connect a chip that acts as the host via UART or USB or even SPI through the actual controller. It's been qualified multiple times, and the last one when we qualified everything was 114, but after that there's been separate qualifications for many of the components. We also have been selected by the Bluetooth Special Interest Group to become their reference stack when they do training materials, for the training materials, something that we're proud of, because the fact that they're using an open source project, and Zephyr in particular, to show the Bluetooth developers how to write applications, how to best use the technology is obviously something that we're very happy with. The controller in particular is a piece of software that was originally contributed by Nordic, but since then has seen a lot of growth and collaboration and contributions from many others. And it's a second generation. We almost rewrote it from scratch. And in this generation, we split the controller into upper and lower link layers so that it better adapts to multiple architectures. And in fact, we're really happy with the fact that it can run today on at least 3 different ISAs, 3 different architectures with 3 different radios. So it runs on, obviously, on ARM, Cortex-M, using the Nordic radios, but also on the Vega board using the RV32 M, if I'm correct, RISC-V architecture, and then also a proprietary radio and ISA that is currently being implemented downstream. It also supports big and little endian architectures, and in general, what makes this controller a little bit unique when compared to the other open source controllers that are out there is the extremely efficient radio utilization it has and the resilience it has to latency, to introduce latency. So we have a latency that's approximately 10 times a resilience to latency that's approximately 10 times bigger than what it used to be in the first generation. So this is something that's obviously also in active development and adding more and more features as we speak. One of them being Bluetooth Low Energy Audio is our cross channels, which is being worked on right now. Zephyr also has a USB device stack, which supports many of the MCU families that Zephyr runs on. It has USB 2.0 support, obviously, but also full and high speed support, and many of the classes you're used to working with, CDC, ACM, and Ethernet, and the mass storage, and so on, and also audio now, actually. This is a stack that was developed also from scratch for Zephyr, and it's currently ongoing a little bit of a refactoring. So if you're interested in USB and want to contribute, we have a topic branch in the repository that you can send pull requests against. Next, Zephyr can also run as an application, essentially as a Linux application. We call this native POSIX. It's a bit misleading, the name, but essentially what it means is you build Zephyr to be a Linux application. This is very useful because it allows you to debug almost everything, so including the kernel, drivers, obviously the application itself, but also much of the code that typically is included in an embedded build of Zephyr, and you can debug, run, and profile that as you would a normal Linux application. So you get all the tools that you typically use for that, like FileGrind and gperf, and all of that can be used to basically reduce the turnaround time when it comes to building and then running and debugging your application. Instead of having to flash it, you just run the executable on Linux, debug it, recompile, and so on. So it's very useful, and this is something that has seen a lot of adoption, and we're seeing now contributors adding simulator for SPI, for GPIO, for I2C, so that you can even build applications that communicate with external hardware, obviously virtually through using the simulators. So this is another area that's under very active development in Zephyr if you're interested. And then we have also a POSIX API in Zephyr. It's not completely complete as of now. So again, we're looking for contributors here. It has a good subset of POSIX though. It's a very carefully selected subset, so that the most important bits and pieces of the POSIX standard are covered. But we're looking to expand it. So this is something that we want to work on in the next two releases to improve and extend the range of APIs that we cover with this. But there's also much more. It has a very powerful logging subsystem with a lot of backends, including things like RTT, and it actually can be configured at runtime to filter the different logging modules. It will also have a shell that is also powerful, that allows for dynamic configuration of subsystems, that allows for, it has even advanced features like autocomplete, like interfaces with the logging subsystem as well. It's a little bit more advanced than what you typically find on an embedded operating system. We have device firmware update provided by multiple mechanisms. We have MCU Manager, which is an external project that we have contributed a lot of code to, that allows you to update your firmware via UART, Bluetooth Low Energy, or TCP/IP. We have Update Hub, we have Hawkbit. We have also display support via LVGL, another very interesting open source project that we integrate into Zephyr as an external module. We have a bunch of file systems and storage mechanisms. So if you don't want a fully fledged file system, you can use one of our storage mechanisms. We give you obviously non-volatile storage without the overhead of files and folders, C++ support, and much more. I really encourage you to go through the documentation in Zephyr. Our documentation website is pretty complete, and you'll find information about everything that I've talked about here and much more. So with that, I'll say bye, and I'll be available for questions a little bit later. Thank you, everybody, for watching.
My name is Martibo Levar, software engineer at Nordic Semiconductor. I'm here to talk about Zephyr development using West. So West is a standalone command line application which has some built-in features for managing a workspace. We'll talk a little bit more about what a workspace is in a minute. West is also extensible, which means that you can write plug-in West commands. Zephyr uses the workspace control features in the build system to integrate source code from multiple repositories. It also provides West extensions for application development. Let's look at what this means in a bit more detail. Like I mentioned, West has some built-in commands for creating and configuring workspaces. A West workspace is just a directory with some Git repositories and extra metadata inside. In this case, these repositories are the main Zephyr repository and some additional third-party libraries and other code with Zephyr integration. Now, Zephyr also provides some West extensions that make it more convenient to build, flash, and debug Zephyr applications. Both of these are optional. You can use Zephyr without West. We won't cover that in this talk, but you can see the West documentation, which I will link to later for more details. Now let's look at some important files in a typical Zephyr workspace. You can see that workspaces have a top-level directory, or topdir, which in this case is called Zephyr project. The topdir contains this .west directory, which marks the location of the topdir and contains a configuration file. In addition to that, every workspace has a special Git repository, which is called the manifest repository, which in this example is the Zephyr repository. And the configuration file says where the manifest repository is. Now, the reason why this is special is because it contains a manifest file, which in this case is west.yaml. Manifest files tell West what other Git repositories should be part of the workspace. A fully populated Zephyr workspace will contain additional repositories, which West is going to clone according to configuration in west.yaml. Now, in particular, modules are a really important part of any Zephyr workspace. A module is a library of third-party code with Zephyr integration. That can include things like file system support, vendor HALs, cryptography libraries, etc. All right, those are the important things you need to know about what WEST does. For detailed documentation, you can see the WEST guide in the link on this slide. And if you've got it installed, you can also ask WEST for top-level help and for help on a particular command at the command line. Okay, that's the last slide. Now let's move on to a live demo. Okay, here I have a Visual Studio Code window, which is showing a Zephyr workspace that I already set up. The Zephyr project documentation has a Getting Started guide, which explains how to do this. Inside the workspace, you can see the .west, modules, and Zephyr directories. Notice though that the actual module Git repositories tend to be nested a little bit inside of subdirectories. Okay, now let's open up a terminal and run some WEST commands. First thing I'm going to do is run WEST help. As you can see, it includes a line or two about each of the commands and what they do. This includes the built-ins for managing the workspace and the extensions for developing with Zephyr. Next, I'm going to run a plain WEST list command, which is going to print metadata about each of the Git repositories in the workspace. This is quite a lot of output, but each line is just the name of the repository, its path within the workspace, the Git revision to check out, and the remote URL to check out. Since that's a lot of output, though, I'm just going to run another WEST list command, which is going to restrict its output a little bit. The format argument here is used to select the metadata that I want to print. In this case, I want to print the name, path, and revision of the module, and then I'm going to give the name of the module, which in this case is CMSIS. So as you can see, there is a module at modules HAL CMSIS, which is going to be updated to this revision when WEST updates the workspace. Let's see how this is set up in the Zephyr west.yaml file, which I mentioned in my slides. If I make that a bit bigger, you can see that inside it contains a list of projects, which are Git repositories, and the metadata matches what we had in the terminal, namely that each has a name, a revision to check out, and there's also a path within the workspace. Earlier in the file, you can see there's some configuration on where to fetch and clone the repository from. Now, these repositories are all on GitHub, but WEST isn't GitHub specific. You can use it with repositories hosted on any Git server. All right, that's a quick tour of the workspace. Now let's take a look at using WEST for Zephyr development. In order to do that, I'm going to change directory to a sample application, which is provided with Zephyr, which is going to allow us to control a file system using the built-in Zephyr shell. The first thing I want to do is build the sample, which I'll do using the WEST build command. You can see there's a board argument here. Every board supported by Zephyr has a short unique name, which is used as an identifier. In this case, the board's name is RealBoard. Okay, so what WEST is doing here is generating a build system first, and it's doing that with CMake. Once that's done, it's going to use the generated build system to actually build the application for my target. Okay, you can see there was a lot to build there. So why don't we take a look at the application's main source file. You may be a bit surprised to see that there's nothing inside main. To see how this works, I'm going to open up the samples.prj.conf file, which is a kconfig configuration fragment, and we'll talk a little bit more about what that means later on. You can see that there's various lines here. One of these is turning on the logging subsystem, enabling the shell, turning on file system support, and doing various other things. The build system parses this file and uses it to compile and link in the libraries which are controlled by each of these individual configuration symbols. Let's take a quick look at a graphical interface we can use to visualize this whole configuration tree. In order to see it, I want to run WEST build again, but instead of using the default build system target, which is just going to update the application as you can see up here, I'm going to run the GUI config target. What this does is open up a graphical view of the configuration tree. I'm going to open up the Subsystems and OS Services and then go down to File Systems. Now you can see there's a line here with a green check next to it which says File System Support. And in the detailed view underneath the tree, I can see that the symbol's name is File System. So the File System option is enabled, which you can see via this checkbox, and that mirrors what we see on line 11, which sets config file system to Y. All right, I don't actually want to change any of these, which I could do with this program. So instead of doing that, I'm just going to exit out and run the sample as is. Okay, so before doing that, I'm going to split my terminal and open up a serial console to the device which is attached to my laptop. Now let's flash and run the application. I'm going to do that using the west flash command. This command uses configuration files and binary artifacts in the application build directory to flash the target. I'm giving it the erase option because I just want to make sure that there's nothing on this device's flash and I'm starting out fresh. As you can see, this command rebuilds the application. In this case, there's nothing to do because we just built it. It's going to mass erase, and then it'll flash the hex file which was left in the build directory. Okay, in the other terminal, you can now see Zephyr boot banner and the colored shell prompt. We can ask for help inside the shell, and it's going to let us know that tab completion is supported, and we should press tab to see all the available commands. Okay, I'll do that. And in particular, I see this fs command, which is what I'm going to use. The sample has some documentation, which you can look at if you want to know how I knew that. Okay, the first thing I'm going to do is mount a file system in little-fs format at the directory /lfs within a flash partition on the device that's been designated for storage. Okay, you can see a bunch of messages popped up. These are all from Zephyr's logging subsystem. You can see that they each have a timestamp, a level, the source of the message, and then the message itself. Now there are some errors here, but those are normal. Because I mass erased the device, there's nothing on its flash, so there's no file system in particular, and little-fs just notices and reformats it. Okay, now that we've got a file system mounted, let's take a look at what's inside of our root directory. It contains an LFS subdirectory as expected, and just to show you a little bit more of what you can do, I'm going to write to a file named foo. I'm going to write the bytes A, B, C, D, and E, F, and then read it back. Great. Now as a final demo, I'll show you how shell commands in Zephyr can take options. In this case, I'll use -O10 to write the byte 12 at the offset 10 from the beginning of the file, and then read it back. And there it is. Let's recap what we've seen so far. We've seen how to use West build, both to build applications and run other build system targets like GUI config, and we've seen how to use West flash to flash applications. We've also seen a little bit of the kconfig interface. On the device side, we've seen the shell, file system support, and the logging subsystem. Let's next take a look at kconfig and debugging in a bit more detail. In order to do that, I'm going to go to another sample application, which is provided by Zephyr, which is an implementation of a solution to the classic dining philosophers problem. This is going to use Zephyr's cooperative and preemptive threads running at different priorities. As before, I'm going to build it for the real board. Since we've shown this before, we'll just skip to the end. Okay, now that that's built, instead of using West flash to flash it, I'm going to use another command, which is West debug. West debug is similar to West flash in that both will rebuild the application and flash it, but West debug is going to bring up a debugger prompt, you can see here, and on the device side, you can see that nothing is running because the target is halted. If I ask GDB for a backtrace, you can see that I'm at zarm reset, which is the reset vector on this target. Next, I'll just use continue to run the sample, and you can see now on the serial console that I have various different philosophers going. What this output represents is multiple different threads running. There are 6 threads in all. Some are preemptible, as represented by this P, and some are cooperatively scheduled. You can see that they have different numeric priorities, and that each one is printing its state when it changes. Let's go back to our debugger and halt the program. Since there are multiple threads running, I should be able to get information about each one, right? That didn't work. Now the reason why is that thread-aware debugging tends to depend on the host software and is therefore disabled by default on this sample. Let's fix that by editing our application's kconfig settings using the GUI config program. I'm going to run the GUI config target again using West build and make some changes. Again, I'll enter subsystems and OS services. Now I'll choose debugging options, and then I'll enable an option which I know is supported by this debugging software. After pressing save, you can see on the terminal that the configuration has been saved to a file in the build directory. Now if I run West debug again, since the application configuration has changed, it needs to regenerate the build system, and then it'll rebuild and reflash it with thread-aware debugging support working. Again, we'll just skip to the end of the build since you've seen this before. Now that we've got our GDB prompt back, I'll run the sample again. And the output is the same as before, but now if I halt the program and ask for information on the running threads in the debugger, I do actually get details on their priorities, where they are in the source code, etc., etc. Okay, next I'll just set a breakpoint and hit it a couple of times to show that this is a standard GDB prompt. Recapping, now we've seen how to update a build configuration and get a debug prompt using West commands. I'll finish up by showing a few more debugging related West commands. The first one is West attach. This is like West debug, except that it doesn't reflash anything. As you can see, it doesn't show the usual lines for updating the device flash and instead just drops directly into a GDB prompt, which is connected to whatever's running on the target. The last command I'll show you is West debug server, which is like West attach, except that it doesn't open a debugger. Instead, it opens a port which accepts incoming debugger connections from elsewhere in the system, which can be useful if you have another GDB interface that you prefer to use instead. Okay, and that's all I have to show you. Thanks very much for watching.
Okay, I think we'll go over to a Q&A now. Marty, Carlos, and Kate, are you ready for the Q&A? Just start
Sure
whenever
thing.
you're ready.
Sure, yes.
Yep. Who's going to MC? Sorry. Well, I can take one. Anil asks, can I use device config tree to map I/O to ADC pin? Yes. In this case, ADC input channels can be configured using the device tree, not kconfig. Arnaud asks, is the custom Python kconfig something that is independent, available outside of Zephyr? Yes, it is. In fact, that's how it began life. Carlos mentioned briefly that we started using it, and then the main developer of that app library started contributing to Zephyr. I see he's already posted a link. That's great. Thanks for the kind words, everybody.
Okay.
So Nicholas asks, for supported sensors listed in the Zephyr documentation, how would you go about configuring Zephyr to be able to use one? So typically the way that you're going to do this is that for your standard sensor that's hanging off of an I2C or a SPI bus, you're going to edit what's called the device tree overlay, which is basically a file that gets mixed into your final device tree. And there you're going to specify what controller you're going to use to interface with the sensor. You're going to mention things like the chip select pin, the speed, etc. Maybe like the I2C device address or whatever. And then there's a device model. It's kind of like the Linux device model, but much, much lighter weight that you'll be able to use to get access to what's called a struct device. And then there's a high-level sensor API that you use to cause the sensor to get the to fetch values, and then you can get them out using a kind of standard structure.
About there's a question by Eli, I think, is that a good reference for porting a board? We have a porting guide that I'm going to link to in a minute. There we go. So that's a board porting guide. You can use that as a starting point, but what I recommend is that you take whatever's closest to your board that's already supported in Zephyr, copy that folder and start modifying. But using the board porting guide certainly helps. Another one that I wanted to quickly comment on is the MicroPython support. Yes, indeed, it's supported. MicroPython is supported. The port is actually in MicroPython itself, the port to Zephyr. So it's part of MicroPython. So when you download MicroPython, you download Zephyr separately, then you can build MicroPython for Zephyr.
So Ravi asks what IDEs are supported in Linux. For upstream Zephyr, there's no real requirement for any particular IDE. I know we do have an Eclipse plugin, and there's official documentation for debugging in Eclipse. In the NRF Connect SDK, we have Sega Embedded Studio Nordic Edition. I know that people use various things ranging from basic text editors like VI and Emacs all the way up to VS Code on Linux. So there's a wide range of answers.
About monitor mode debugging, as far as I know, no. We do support obviously SWT via JLink and DAPLink. We do support a few other features that are sometimes specific to a particular debugging system or mechanism, like RTT. But as far as I know, there's no support for monitor mode debugging. No.
Ellie asks, how does the Zephyr footprint compare to a similarly configured embedded Linux footprint? The Linux footprint is going to be much larger than Zephyr, I think, and it's a question of what other peripherals you're enabling.
Yeah. To follow up on the, it's scrolling very fast, but what is supported is semi-hosting. I just realized that it's not the same as monitor mode debugging, but semi-hosting is actually also useful, and there's basic support for that in Zephyr. NR53 is perfectly fine to use with Zephyr. Yes, it's safe for gateway or for whatever application you have. NR53 is fully supported in Zephyr. Regarding the audio over BLE, so the basic functionality for the host side of things is already in the tree. There's a lot of work ongoing in a separate private repository because it has to be done in that way due to the confidentiality nature of the specifications that we're developing against. But I would say during this year and early next year, we should see at least a functional starting point of BLE audio in Zephyr.
I don't believe, so Jurgens is asking about Zephyr being supported in QLU Vision. I don't believe it is at this point.
No, it's not. And honestly, I don't think it will be because Microvision requires its own build system, and it's not non-trivial to port. There is work, however, ongoing to have support in IAR, if you're interested. IAR itself, they're involved. Matthew, you want to take the QEMU one?
Oh, yep. Sorry, I was pasting an answer for ADC. Where is the QEMU one? Sorry,
So
what about QEMU
is,
emulation? Yeah, it's supported right now. It's available in the Linux SDK. There's QEMU builds for all the supported architectures, and I believe that's also something that's in the works for other platforms. Is it possible to change the function of a peripheral during runtime? Not right now, as far as I know. Carlos, you can correct me if I'm wrong. Not like official support?
No, not right now, no. Just trying to... if a vendor is providing an SDK, why would someone use Zephyr instead of that? That's a good question. That depends on how the vendor actually packages that SDK and how often that SDK is updated with upstream vanilla Zephyr. So if that vendor provides something that's very up to date with the current Zephyr and all the features you need are already included in the SDK, I would say that's very little reason to use upstream Zephyr. There's also the fact that if you that many vendors will ask you to contribute fixes or corrections directly to upstream Zephyr. So if they're merged there, you will see them reflected in your own tree earlier, because obviously having an SDK based on that upstream Zephyr means that there's a delay, a propagation delay. But other than that, I'd say in general, using the vendor SDK, as long as it's properly packaged and maintained, updated, is probably the better, your best bet.
Yeah, I'd say look at making sure that the vendor is keeping up with the security updates too.
Yeah.
So Luis asks a question about managing an external library using kconfig. There's actually a sample. There's a variety of different application development samples, actually, which I'll just give a link to, which cover various use cases related to that.
Okay, we are at 1 hour now. So how about we answer a couple more questions and then we'll wrap it up.
Okay, can try the current ARMA Cortex-M series supporting the user mode and kernel mode through software interrupt. It supports, so Zephyr has support, as I was talking before, for user mode, and that will use the Cortex-M feature, the supervisor mode in the Cortex-M. We do use software interrupts to switch for system calls. So the answer to your question is yes. Just another one for Lucas, using SPI2C on NRF52, whether you use the Zephyr API or the NRFX libraries directly, since NRFX is included with Zephyr, that's up to you. Both have advantages and disadvantages. If you use the SPI2C, well, the API is probably simpler, and you can then switch or port your application to another chip in a much easier way. You don't need to change APIs. NRFX will give you finer grade control over the hardware. So that's really up to you and your application. Maybe someone else wants to take some other one.
Yeah, I'm going to have to drop right now, but
okay.
Elon was asking about what's the best approach for maintaining a board. I'd say basically merge it to the upstream Zephyr, because that way it'll be kept current.
That's by far the easiest, yes. Yeah. That's by far the simplest, because then it will be maintained for you. Wherever change is made that requires changes in your board, whoever makes that change will fix your board as well. So that's the easiest. If it's confidential, however, we have full support for out of 3 boards, out of 3 architectures, and out of 3 SoCs. So you can basically have that can live in a separate repo, and but obviously you'll have to maintain it yourself. Martin, maybe Chris's question would be good for you.
Sure. Is there a visual way to see the device tree? Well, so right now what you need to do is take a look at the final device tree source file, which is going to be populated in the build directory. And then what you can do is compare that to the available bindings. So basically your SoC vendor will provide a full description of the hardware that's available on the SoC, and your board, if you're using a development board, the same will be true for any additional sensors or anything like that. And you can compare that to what's called device tree binding files. And those are kind of a schema for what the nodes in that device tree can contain, as well as documentation for what is available and how to configure it. And then there's a bunch of additional documentation for, for the language and etc.
Okay, Marty and Carlos, do you have any last comments?
Just one is that for everybody who wants more information, please feel free to join our Slack, Zephyr Slack, and also our mailing list. You can find links to both in our main GitHub page. I'll link to that as well, because that's one of the best forums to get questions answered. Both of them, actually.
Okay, I just have one short comment. Thank you, Marty and Carlos and Kate, for that very informative webinar. We will share the recording and the presentation on webinars.nordicsemi.com, and we'll most likely also include the Q&A. In addition, if you did not get your question answered, you can always ask a question on Nordic DevZone. That's devzone.nordicsemi.com. And also, lastly, feel free to check out some of our other webinars. If you go to nordicsemi.com/events, you'll see the next webinars. Feel free to sign up if you want to. Again, Marty, Carlos, and Kate, thanks a lot. And I hope you all enjoyed this webinar, and have a nice day. Thank you. Bye.
Thank you. Bye.
Bye-bye. Thanks.